Good morning, everyone. Yesterday we have studied in part 1 about the controls and all the control surfaces, the primary ones. Today we will study about the secondary or the auxiliary control surfaces. So, the secondary or the auxiliary control surfaces are the ones which are used to actually control the or actually helps in controlling the primary control surfaces. So, the force of the air against a control surface during the high speed of flight can make it difficult to move and hold that control surface in the deflected position. So, due to that, a control surface might also be too sensitive for similar reasons, and several different tabs are used to aid with this type of problems. Okay, so a tab is basically a type of a device which is a very small aerofoil structure which are fitted on all the primary control surfaces to control them easily. Okay, so by a small deflection of the tab, the control surface will deflect in the opposite direction. If a small part of control surface, if that is called as a tab, and if the tab is moved in, let's say, in the left direction, then once the air strikes that tab, so that will push the control surface in the right direction. So depending on which side we are trying to move our control surface, the primary control surface, according to that we have to put the tab in the opposite direction. Okay, just like this, that if we have to turn our, let's say this is the control surface. Okay, if we have to turn the, and there is a tab like this, a part of it, if we have to turn this thing either maybe in this direction, okay, that is, let's say, in the right direction or maybe in the left direction, then this tab has to be moved in the opposite direction. So once, if you imagine in this way, if the tab turns in this direction, so when the air will be coming and striking this, okay, then that will push the entire span of aerofoil structure or entire span of the control surface to move in the opposite direction. Okay, so that will basically help the pilot in controlling or moving the huge control surfaces which require a lot of mechanical power. So you can see over here in this picture there is a ground adjustable trim. This is a sort of a trim tab that is used in the rudders. So among many type of tabs, there is a tab which is called a trim tab, and it is used to trim the main control surfaces to a certain angle. Okay, and it may be ground adjustable, or it may also be, in modern aircraft, it may also be electronically operated and mechanically actuated type of trim tabs which you can control from the cockpit itself. And then we have got balance tab. Balance tab is exactly just like the trim tab that acts in the opposite direction, but they are mechanically linked to the primary control surface in such a way that when the primary control surface is moved, the tab will be moving in the opposite direction automatically. Okay, the tab will automatically move in the opposite direction to help the primary control maintain its position. Okay, so this is the picture where you can see it's written that the tab geared to deflect the proportionally to the control deflection but in the opposite direction. So this is the tab, this is the tab. Okay, so that is going up. As you can see, the arrow is marked, that is going up in order to put the, and if that is going up, then the air load will be putting this main control surface down. So if we have to move the control surface down, then we have to move our tab in the upward direction. So this is mechanically fixed, so it will automatically happen. If you have to move the main control surface, the tab will automatically go in the opposite direction and the main control surface will come in the other direction, just opposite to the tab direction. Okay, so they basically help in what way? They help the primary control surface to maintain its position, so that you don't have to again and again move it, or you don't have to find out all the ways to hold it in that point. This tab will actually help the main control surface to hold them in their particular position. Then we have got servo tab. This tab is used to actually move the primary control surfaces, as they are mechanically linked when hydraulic power fails to move the primary control surfaces by manual control. So this is used either as a primary or as a secondary unit, which moves in the opposite direction like trim or balance tab. This also moves in the opposite direction, but it is, as you can see, with some mechanical linkages and control stick, it has been made in such a way that when mechanical failure or rather hydraulic failure will take place where you cannot actuate your primary control surface, at that time you can just move the tab. The tab will be moving the entire control surface. So moving the tab will be easier at that time by mechanical force, because tab is a smaller surface, less air load on that. Okay, so that will be helping in moving the entire control surface without even hydraulic power when there will be hydraulic power failure. So that will not allow you to lose the control of the aircraft. Then we have got anti-servo tab. So by the name you can understand, so this is acting just opposite to whatever the other tabs are working. Okay, whatever trim tab, balance tab and servo tab is working, this is just opposite. These are working in the opposite direction, or rather you can say that they were working in the opposite direction to the primary tab. This is working in the same direction of the primary tab. Okay, over picture also you can see over here that these are anti-servo tab is given. Okay, and they are working in the same direction. Same direction means in the direction of the movement of the primary control surface. If this is the primary control surface, okay, so the tab will also be moving in the same direction. If this is moved down, then the tab will also move down. Okay, it is not the case of the just like the other tabs. So now let's read what is this. This moves in the same direction of the primary control surface to increase the load which could be felt by the pilot operating the aircraft for his or her better idea about the controlled movement of the primary surface, which means that it is to give some effective feeling in the arms of the pilot or in the hands of the pilot, which will make him or her feel about to what extent they are actually moving, what load is actually being imposed on the control surface, so that they don't move it too much. Okay, so this is like a resistance offered in the motion of the control stick. Okay, in order to give a feeling of to what extent they are actually moving the tab. Next we have spring tab. Spring tab is also just like the trim, balance and the servo tabs. They also moves in the opposite direction, but they have got a spring attached to them, which does what? That increases or enhances the input of the primary flight control surface after it has deflected to a certain extent to aid the pilot or help the pilot in moving the same at high speed. Okay, at high speed we require a lot of mechanical power because huge air load will be imposed on those control surfaces and the tabs, so that will be very difficult for us to move. So for that reason this type of springs are attached which will be pushing the primary control surfaces and the tabs at that time by the help of mechanical force offered by the spring. Okay, next we have mass balance. So what is this mass balance? Mass balance is type of a balance which is, all those tabs were aerodynamic balance. Okay, aerodynamic balance means they used to move in some direction, maybe in opposite direction, and the other way the primary control surface used to move. But in mass balance what we can actually see is that as control surfaces have a tendency to flutter during operation, so it's CP. CP is the center of pressure where the aerodynamic lift acts. Okay, it is a center of pressure where the aerodynamic lift acts and is kept aft of the CG, where the entire weight of the body acts, or the entire weight of the control surface acts. So that is something that balances the fluttering. And to further put CG forward, an added mass can be attached to the control surface, which you can see marked red circled, encircled, which will be doing what? Which will be shifting the CG more from the CP. So this is called mass balance in a design. So I'll just show you what is this basically. See in the picture over here, this is the control surface. Let's say this is a flap, for example, and this extra mass has been added towards the leading edge of the flap in order to shift its CG forward. Let's say the CG is here. So now due to this weight, extra weight going forward or attached forward, the CG is shifting forward. Let's say it's coming over here, for example. So if the CG comes there, then what will happen? The loads that will be imposed like this from the top and the bottom surfaces due to the air fluctuating, the airflow fluctuating over there, so that will not impose a lot of stresses, because the CG is always at the already at the front side. Okay, over here also you can see there is one more, so they will be balancing them as the weight has gone forward, so they will be balancing the fluttering action. So that is called mass balance, that by adding some mass you are actually balancing the fluttering action of the small aerofoils. Now after that we have got high lift devices. These high lift devices are used in order to create more lift when that will be required during either takeoff or maybe landing. During takeoff we'll need obviously more lift, so we can actually take off from a small landing runway, or with a small landing run we can actually take off easily. And during landing we need this type of high lift devices so that the speed is reduced and we get a controlled or a balanced descent towards the landing runway. Okay, so the first thing that can be actually used is a flap, and flaps are just like the control surfaces that we are fitted like ailerons. They are fitted in the inboard trailing edges. Okay, ailerons are usually fitted in the outboard trailing edge and they are fitted in the inboard trailing edges, and their purpose is to only go down. Okay, they only go down, they don't go up and down just like aileron. They only go down in order to increase the camber. Once the flap, let's say this is the wing and this is the flap, if that goes down, then you can see the camber increases or the entire surface area increases, so that increases more lift, so more lift, as well as you can see is if this is going down, then it is also, the air is also striking it like this, so that will also decrease the speed. So what happens, the lift increases and the speed decreases, so that allows our aircraft to have a controlled or a controlled movement. Controlled movement means it will be very easy for the pilot to actually control during the takeoff and the landing phase. So flaps are found in the inboard trailing edges and also in the form of leading edge flaps are also there. So leading edge flaps are usually flush to the bottom surface. We will come across what are those things. To increase the camber of the wing, that is the effective surface area. If you increase the effective surface area, the total surface area, so that will be increasing more lift, because we know that lift is dependent on surface area. So that will also reduce speed. So it is best for takeoff and landing phases and requires shorter runways. So you can see over here the flaps are deployed in this picture. There are many pictures given. Then what are the degree of movement of the flap? It can extend up to 45 to 50 degree maximum in some cases. And the leading edge flaps, which moves from the leading edge, just like in the picture you can see. So this is the flap that has come down from the leading edge in order to increase the leading edge camber also. So those are called as Kruger flaps. And the material used is aluminium or maybe composite in some cases. And the flaps are of various types with different angles of operations and uses. Then we have got types of flaps. What are the types of flaps? There is a plain flap, which is just like in the picture number A, you can see there is a plain flap that is a part of the wing itself. Okay, and that comes down in order to increase the camber and lift. Then we have got a split flap. Split flap is what? It is a part of the wing, but it is, you can see, it is actually having a split mechanism. That is, even if it is coming down, the upper top surface, the upper top layer of the wing, that is not deflecting. Over here, this was the full part of the wing actually. So if that goes down, that means the wing entirely bends like this. But over here, you can see in the split flap, the mechanism in the split mechanism. So the entire aerofoil remains same, but there is a lower portion hanging down, which is called as the split flap, and that split flap is actually doing what? That is increasing the camber from the bottom surface in order to increase lift and reduce speed. Then we have got a Fowler flap. Fowler flap is utilized to increase the chord as well as the camber, because as you can see there is a gap between the flap and the main aerofoil in the Fowler flap case. So that is doing what? That is increasing the chord, which is not the case for the other two, and at the same time it will go down to increase the camber as well. So that will be increasing more surface area, as you can see. That will be increasing more surface area, so that will give us more lift, and also there is a small slot that gets created from here, and the air flows like this. Air will come from the bottom surface and it will flow over this surface, because when the airflow will be separating from here, it will not allow the airflow to get separated so easily, because when the airflow after coming or reaching this point will try to separate out from this surface, that will cause more drag and less effectiveness. So in order to reduce that, this slot energizes some amount of fluid from the bottom surface to go and wash away those turbulences and take them along with it, like this. Okay, so that basically energizes the boundary layer or the disturbed layer which is on the top surface or the upper surface of the wing, so thereby decreasing drag and also increasing lift. Then we have got slotted flap, which are separate aerofoils attached adjacent to each other, and there may be a number of like 3 and even more in some cases if it is required by the manufacturer, to increase maximum camber and to resist flow separation. You can see in this picture, so there is a fore flap, the first one, then there is a mid flap, then there is an aft flap. Okay, when they are retracted, then they form the part of the wing itself, just like this, you can see. And when they are actually stored down, then they become like this, increasing the camber and decreasing speed and increasing lift. Okay, and they too have, you can see, they too have slots or gaps made like this, which actually energizes the boundary layer, as I have said already in case of the Fowler flap. This is the same thing, so that minimum drag and maximum lift is produced. So the trailing edge flaps work together with the leading edge flaps for better lift and more camber, and usually lowering the trailing edge flap also lowers the leading edge flap. They work together in maximum cases, and all flaps form a part of the wing aerofoil when they are retracted. Okay, they basically become the part of the wing when they are all retracted. Then we have got mixed controls. So now, if a primary control surface is having a mixed control, okay, or a mixed operation with a high lifting devices, just like over here we can see that the aileron and the flap, they are fixed together. The aileron and the flap, they are fixed together in one unit, and they are known as flaperons. Okay, and you don't have to give single input. You can give different input to it. If this goes up, this will be acting as an aileron. If this goes down, this will allow the aircraft to generate more lift. So they are basically working in both modes. They are working as an aileron as well as an flap. So that's the reason they are called as flaperons. So in the same way, we have other structures as well, where we will see rudder vetters and ELEVONS. So there will be also mixing controls. When we will come to that thing, I will tell you. Now next, see, there is a high lift device, which is a very simple device. It is called as slat, which is usually fitted in the leading edge, and that increases the leading edge camber, and that also does what? That energizes the bottom surface fluid. You can see by the arrow it they have given, that energizes that bottom surface fluid, and that passes over the upper surface of the camber. So when during climb the angle of attack is more, so there will be more disturbances created like this over the top surface. Okay, so in order to wash away these disturbances, you require some sort of a gap to be made, so that a high speed airflow can actually go and wash away all these like this. Okay, so that's the reason this type of devices are used to control the boundary layer in a better way. Next we have got slot. Slot is exactly the same type of a thing that has actually created in the slat. Okay, this is the gap, you can see there is a gap. This is also fixed in the leading edge, and it's a fixed device mounted to extend the leading edge of the wing forward or downward, and is known as a slot or cuff. and the slat is also used in partial form in some aircrafts to outboard section of the wing, where it can keep the ailerons effective when the wing root tends to stall at high angle of attack. Okay, at high angle of attack, this basically allows the ailerons, I mean some part, let's say this is the wing, when it is attached in the leading edges of the wing at the outboard section, and if you imagine it in this way, so this is the wing, okay, and if they go down like this from the leading edge on both sides of the wing, then there is ailerons fixed in these positions in the trailing edges, so that at high angles of attack like this, okay, these leading edges slots will energize the boundary layer to flow properly over these ailerons, so that the ailerons are effective during the stall to control the aircraft. Okay, if they were not fitted, if there would have been a normal aerofoil structure like this, and if that actually moved like this during a climb or a stall action, then the airflow would have gone like this, and it would have made this type of disturbances, and the aileron which is fitted over here, that even if it would have moved up or down, it wouldn't have got that much of proper airflow over them to actually give a proper control, okay, which that they can give when laminar air flows over them. Slot is created, so when a slot is created, that slot energizes high speed air to flow over the aileron surface and allows the aileron surface to work properly. So that's the basic logic. Now next we have ELEVONS. Just like we have studied about flaperons, in the same way you have got ELEVONS, where the ELEVONS perform the combined functions of the ailerons and the elevators, and they are typically used on aircraft that have no true separate empennage, such as a delta wing or flying wing aircraft, and they are normally not used in civil transport aircrafts, and they are installed on the trailing edge of the wing, and they moved in the same direction, and the ELEVONS cause a pitch adjustment, okay, and as well as a roll adjustment as and when it is required. So when they are moved in opposite directions, the aircraft rolls, and the ELEVON may also move differentially in the same direction, causing adjustments to pitch and roll together. Okay, so depending on the input from the pilot, these ELEVONS can actually, you can see it's given here. Okay, they don't have any separate elevator and separate ailerons. The same unit acts together as a mixing control. So the control stick or the yoke activated ELEVON movement through a mechanical or electronic mixing device. Next we have rudder waiter. So this is also another or the third mixing control or mixed control, in which the rudders also act as an elevator. Okay, and these are known as V configuration, because this looks like a V, capital letter V. So the upward and the outward movement, the upward and the outward from the aft fuselage, they are fitted, and they have got a V configuration, and each contains a movable rudder waiter built into the trailing edge, and they are usually used to move the aircraft about horizontal axis and or vertical axis. Okay, about horizontal axis, what is given? Pitch is, we get the pitch by the help of the elevator action of the rudder waiter, and by the rudder action of the rudder waiter, we get the yawing action. Okay, next we have drag inducing or speed reducing devices. Now we have studied about the lift increasing devices. Now we need to also know about the drag inducing or the speed reducing devices in order to decrease our speed when we have to land. So spoilers, by the name we can understand, this is a type of a device that reduces the lift and increases the drag, and they reduces the speed of the aircraft in flight, and the spoilers are sometimes called as the lift dampers because they decrease the lift. Okay, and they are normally acting together or act together with the ailerons to control the aircraft at low speed. At high speed it is not required. The ailerons are capable enough to roll the aircraft when needed. Then we have speed brakes. So they are fitted at the upper surface of the wing. They decrease the speed of the wing before landing, and when thrust reversers are activated, thrust reversers, they are fitted in the engine. They reverse the thrust, they change the direction of the thrust in the opposite direction. The thrust do not act in the forward direction anymore, it acts in the reverse direction to retard the speed of the aircraft. So when these thrust reversers will be activated, so along with that the speed brakes will also automatically get activated. Okay. Then there is a very important thing which is called as the boundary layer control. Now what is this boundary layer control? This boundary layer is basically, you can see in the picture, that when the air flows over the aerofoil, if there is a laminar flow or the aerofoil is at a normal angle of attack or very low angle of attack, then it is normally flowing. But when the angle is increasing, when this angle is increasing, then the airfoil, after reaching the leading edge, to some extent it will go, then it will get separated from the surface and it will cause disturbances or turbulent airflow, okay, which will decrease lift and increase more and more drag. So in order to make this aircraft go up, or maybe you can say in order to increase the angle of attack as well as to have laminar flow over them, we are actually utilizing some sort of boundary control or boundary layer control, which allows us to give a smooth or laminar flow over the top surface or the upper surface of the wing. And this layer that gets created above the wing is known as the boundary layer. Okay, that is why that is called a boundary layer, because you can see there is an imaginary boundary, okay, above which all the flow is laminar, but within this boundary the flow is a disturbed flow, okay, having more drag and less lift. So this particular flow needs to be made smooth so that they do not cause so much of disturbances. So laminar or smooth layer of the air with no disturbances or no intermixing of particles is observed up to about half the chord of the distance from the leading edge, which is also responsible for lift production. But as flow proceeds further, the layer of air now becomes very slow or sluggish, okay, and they sticks to the, and that particular air or the layer of air sticks to the upper surface, and due to friction or adhesion is a type of a force, it is a adhesive force, it's like a sticking force, it's just like gum. So the air molecules actually sticks to the surface, so they thereby what happens, that does not allow the other top layers to also proceed further, okay, the other top layers that will, if there is a flow which is very slow which is passing over the surface, that will also not allow the other top layer to move fast, that will also retard the speed of the other top layers, the top layers will also become very slow. So that causes to create the boundary layer, okay. So that particular slow stream of layer needs to be moved with proper energy, and those techniques which we will utilize to move that sluggish air will be called as boundary layer control, which we will be studying next, and their methods. So there is one more thing left over here in this slide, it is the transition point. So what is the transition point? It is the point where the airflow separates the wing surface, okay. So after there is a laminar flow, when the airflow actually separates the wing surface, that is a point which is called as the transition point. Why transition? Because now the laminar flow is in a transition process, or is in a medium process where it is actually getting converted into a turbulent flow, okay. So that is called the transition point. So now we have got the boundary layer control methods. So what is the boundary layer control method? The very first thing that we have is a vortex generator and small aerofoil strips. These are the small aerofoil strips which are normally aluminium, made of aluminium, and they are mounted on the top wing surface very close to the leading edge. That energizes the sluggish boundary layer to pass smoothly over the surface, okay. So you can see these are the sections, these are the aluminium strips. Over here also you can see in this picture, okay. That does what? They energizes the boundary layer so that they don't actually stop. So whenever the boundary layer will come like this over the wing surface, so they will allow the air to pass through them and they will become more energized. So there will be this type of structures as well, and as we know that any convergence sections like this increases the speed. Okay, that increases the speed. As per Bernoulli's theorem, we know that convergence sections increases the speed. So whenever the sluggish layer will come through these small aerofoil strips, their speed will be increased and they will not be leaving the bound surface anymore, and they will be having more speed now, and they will be energized and they will flow over the surface very easily, like this. They will flow over the surface very easily. Okay. Then we have the same type of thing, which is called a wing fencing, but this is not a small strip, this is a long strip, and the purpose of wing fencing is not to allow any chord-wise flow. Chord-wise flow means the flow should always go from the leading edge to the trailing edge, right? From the leading edge to the trailing edge. The flow should not come like going in this way and then turning that way. So those type of disturbed flows or chord-wise flow, this is called chord-wise. This is not chord-wise flow. This is the chord-wise flow that we require, and any span-wise flow like this is not allowed. That will not give us any sort of a lift. So in order to resist that, we use small barriers like this, which allows only smooth lamellar flow or chord-wise flow to take place over the surface, which are called as wing fencing. Then we have got stall edge. Stall edge are the small strip or wedge like structure fitted like this in the leading edge. Okay, that does what? The span wise to the leading edge, in a span wise it is fitted in the leading edge to make the root stall first. Okay, so in any aircraft, if so, this, let's say this is the wing, let's say this is the dihedral. Okay, this is the fuselage. So if the root section stall first, that is the root will come down first, then the tip section, and the tip will still have enough lift to actually hold its place, then there will be one advantage. What is the advantage? As we know that the ailerons are fitted in the outboard tip section of the trailing edge. So if the tips do not stall before the root, if these tips do not stall, then they will still have smooth flow flowing over them, which will give them a better control for these ailerons. Okay, that will give us better control by the ailerons, as when the aircraft root will be going down, but the tip will not go down when it stalls. Okay, that is the reason you will find that the angle at the root is more than the angle at the tip, just like this. Angle at the root, this is more, but slowly when it comes down to the tip, you will find the angle is normal. Reason behind that, with a greater angle at the root, already when the aircraft will stall, means when its angle of attack will increase more, the root section will stall first as compared to the tip section, which will be this at that time. You see, the tip section is not yet having that much of angle of attack as compared to this root section, right? It is having more angle of attack like this. So that the root will stall first and the tip will stall afterwards. So the tip which is stalling afterwards will give us the effectiveness to control the aircraft. So that's the reason these type of things are kept, and they allow smooth flow of air over the surface of the ailerons to control the aircraft during the stalling period. Then we have got wingtip vortices. Now what is this wingtip vortice? This is a very important thing, very important thing. Why? Because these are drags which does not allow the aircraft to move forward, which are caused normally at the wing tip. You can see over here, when the air flows like this over the surface and it goes like this at the wing tip, you will also find there will be air which will be flowing from the bottom surface as well. But now, as we know that the below surface is having high pressure and the upper surface is having low pressure. So the tendency of the air is to rotate like this from the high pressure to the low pressure region at the wingtip. So when the air like this will be rotating from the high pressure region to the low pressure region, they will be causing vortices like this, which will be going back in this way. Why? Because there is a forward velocity of the air as well, which will allow the vortices which are created at the wingtip like this to push backward, and this is basically a disturbed airflow or a spiral disturbed airflow, you can say. They are in a spiral form. Okay, they are rotating as well as moving backward. So these vortex will allow more drag to produce, and that will decrease the lift as well as the speed of the aircraft. So in order to reduce that, we will be actually attaching some sort of a technique in which we can see, this is called as winglet, which are fitted on the aircraft. You see there is an aircraft without winglet and there is an aircraft with winglet. So aircraft with winglet and aircraft without winglet. So vortices are produced. Here is no vortices, weak vortices which are going back. Now how this is taking place, I will show you. See, if we have this type of a winglet at the wingtip, then and imagine this is the leading edge, okay, and there is a trailing edge like this. So when the high pressure air will be coming from here and try to go at the till the top of the winglet and then come and fall over the upper low pressure surface, okay. So you see now the distance has increased, which was not the case when it was not having any winglet. Now as this distance has increased, we have increased the length of the wingtip now. So this has to travel a longer distance now in order to go in this direction. So by the time the forward velocity of the air is actually pushing these vortices backward, by that time it is reaching the top of the wingtip and then again falling back to the upper surface. By that time it is getting more time, the forward velocity of air is getting more time to push this vortex or push this disturbed airflow and put them backward. So now we know that any flow of air that is going backward, okay, any flow of air that is going backward is acting in the reaction direction or maybe in the direction of the engine output, just like engine exhaust. So if that is acting in this direction, so naturally there will be a reaction force or a thrust force acting in the other direction. So previously the vortices that were created at the wingtip was a negative thing for us, okay, that is to increase more drag and decrease the lift, decrease the speed. But now that we have moved it in a smarter way, towards the back side by the help of winglets, so now that is rather acting as a formula for thrust, okay. Now rather that is helping us in the opposite direction to move forward, because whenever the velocity will be now moving in the rearward direction, so that will have a reaction, and the reaction will be what? Thrust. Just like in case of engine, we know engine's thrust goes backward and we get a forward velocity of the aircraft. So in the same way, these vortices are now converted into a positive mode instead of a negative mode by the help of the winglet, okay. If you read these two slides, you will come to know what is the vortices and what is winglet and what are the purposes and how they are made. Now there are high speed flights. So what is high speed flight? High speed flight is any flight that takes place at the speed of sound or sonic speed. So sonic speed is basically the speed at which sound vibrations or sound energy travels through air particles or air molecules or in the medium of air, and this velocity increases with the increase in temperature. Thus it also decreases with altitude, because at higher altitude we know that there is less temperature, so there will be less speed. So maximum speed of sound will be available at the below surfaces like where we stay, okay, the lower surfaces of the atmosphere, and as the aircraft proceeds further, so there will be, as it goes up in the high altitude areas, so over there the speed of this sound will be decreasing in air. So normally when any object that is moving, that is causing some sort of a vibration taking place in the surroundings, right? So the disturbances that are caused in the air ahead of the aircraft, when the aircraft is moving forward, the disturbances caused by the air ahead of the aircraft, okay, if this is the aircraft, let's say, and this is the aircraft, when that is moving, it is causing disturbance in the ahead of the aircraft. These are the particles of ahead of the aircraft, which is already alert by now that an aircraft is proceeding towards itself. Okay, so these disturbances actually causes a pressure energy. Okay, the disturbances, this vibration energy actually gets converted into a pressure energy, which increases the pressure of this particular region. Okay, this pressurizes this region, and as we know, air is compressible. So if air is pressurized, so what will happen? They will be having more density, then their density will increase if they are pressurized. So those compressed air will now act in a different way. They will not allow the aircraft to proceed forward with its proper speed, and they will resist the aircraft in moving forward, which will be causing shock waves. Now we will come to one by one what are all these things. So these pressure waves, just know the particular temperature and the speed. So it is 59 degree Fahrenheit, at which the speed of the uh, speed of sound in air is 761 miles per hour. Okay, there may be other units as well. So this unit is given in degree Fahrenheit and miles per hour. Now how is this speed of an aircraft is measured? It is measured by the help of a Mach number. What is this Mach number? This is a ratio basically. Okay, so there is no unit of Mach number. It's just a numerical value, as it's a ratio, and it's a ratio of two speed. What is the speed? The speed of the aircraft. Okay, it is the speed of the aircraft at the top divided by the speed of the sound. Okay, it is the speed of the aircraft, or true speed of the aircraft means the speed of the aircraft at a particular altitude divided by the speed of the sound. So this is a ratio. So from this ratio you can see that if the sonic speed is considered as 1 Mach, then if the aircraft travels with the same velocity of the sonic speed with Mach 1, then the ratio of the aircraft speed to the sonic velocity will become 1. Okay, 1 and 1 will be cut, so there will be only 1 left, right? So that means Mach 1 is the speed which is the sonic speed, and if any aircraft travels at Mach 1 speed, so they are called as they are traveling at Mach 1 speed, or they are traveling at sonic speed. Now normally we have all the aircrafts, all the transport category aircrafts and all the light aircrafts, they travel less than sonic speed. More than sonic speed, which is called as supersonic speed, which is from 1.2 Mach to 5 Mach, and there are hypersonic speeds which is above 5 Mach. So supersonic speed is basically used by the fighter jets. Okay, they require a lot of speed, and the hypersonic speed is usually employed by missiles and some rockets and all these things, which utilizes a lot of speed to leave the earth's surface, to break the force of gravity, or to escape the force of gravity. They require a huge speed, so they utilizes those Mach numbers, those higher Mach numbers. We don't require such higher Mach numbers. Normally our aircraft flies in the subsonic or in the transonic region, and it is about 0.8 Mach for us. Okay, that is a normal Mach, 0.8 to 0.85 normally, and smaller aircrafts don't even reach that also. They normally fly around 0.3 to 0.5 Mach, so they don't have to face any type of shock waves or anything. But any aircraft that is flying very close to the transonic speed will suffer some sort of shock waves or supersonic velocities at some part of it. Why? Just like imagine if there is this wing surface, and we know that at this point the speed increases as per Bernoulli's theorem and the pressure decreases, right? At this point of the uh, aircraft structure, whenever the air is flowing over it, at this point the speed increases and the pressure decreases. So at this point what happens, if there is a transonic speed coming like this, so as the speed increases over here, so the speed over here you can expect that to be already becoming supersonic. Okay, so some part, that's the reason it has been said that some part of the aircraft will be experiencing supersonic speed when even the actual aircraft speed is not supersonic, but some part of it, due to some physical and some mechanical changes taking place over the surfaces, due to just like the as per the Bernoulli's equation. So the speed will be increasing, so that will cause supersonic airflow to be flowing over them. So those areas will be actually suffering from sudden increment in the pressure, so that will actually suffer compressibility effect. Okay, so those areas can generate shock waves like this as shown in the picture, and any shock wave that is actually perpendicular over here, you can see it's perpendicular, it is acting at 90 degree almost. So this type of shock waves will be called as normal shock wave. Okay, and the shock wave can cause the airflow to separate from the wing. You can see it is separated from the wing, it is going away from the wing, and the shock wave also causes center of lift to shift aft. Okay, the center of lift of the aircraft will be going backward, causing the nose to pitch down. So it will not allow the pitch of the aircraft to hold anymore. It will not allow the aircraft's nose to be hold anymore at the at that level. So if the center of lift goes backward, then the aircraft nose will be going down. If the center of lift is going backward like this, then the aircraft nose will be going down. Okay, the lift will be decreasing in the forward section and it will go down. So the speed at which the shock wave forms is known as the critical Mach number. Okay, the speed at which the shock wave forms is known as the critical Mach number. Then we have supersonic flow. In supersonic flow, we know that the flow will be reaching 1.5 to 5 Mach, 1.2 to 5 Mach, sorry, and its entire body faces the supersonic speed. So the flow will be actually going and meeting the last trailing edge like this, and that will form oblique shock wave. Okay, oblique shock wave, and this oblique shock wave will actually cause sonic boom type of thing. Okay, sonic boom type of thing, which is also called as a sound, huge sound produced when oblique shock waves are created around the aerofoil structure. Okay, and behind this wave the speed is still supersonic. Okay, behind this wave the speed over here, this is still supersonic behind this wave. It was already supersonic here when it made the shock wave over here. After that also it did not change, it is still having supersonic speed, and the density and the pressure is still high. Okay, now you can see over here there is an expansion wave. We will come to this, what is expansion wave. We know that when pressure is increased with that high speed of air moving, so that will actually compress the air particles, as air is compressible. So they will have a tendency to always expand. That compressed air will always have a tendency to expand and go away from the surface of the aerofoil. As you can see over here they have given, so they are going away from the surface of the aerofoil. So whenever this aerofoil will change its direction, let's say in this direction, if it goes, if the aircraft changes its direction, so these aerofoils will also change their direction accordingly. So at that time the sudden change of direction will cause the sudden expansion of those compressed molecules of air which were previously flowing over the wing surface to now change and expand and go away from the surface of the aerofoil. Okay, and those type of wave is called an expansion wave, where the air expands from its compressed state. Now we have got swept back wings, which we normally see in any airliner today's world. If this is the fuselage, then they have got swept back wings like this. What is this swept back wing? It is not a normal flat wing or a perpendicular wing. It is swept back wing. At some angle this has been swept back. Okay, it has gone back, and the reason to keep this swept back wing like this is to reduce the sonic speed, and how we can do that? In this picture it will be very easier for you to understand. See, there are two velocity vectors taking place. This is one velocity vector. When the supersonic air is coming and reaching the leading edge, they are broken down into two forms, one going this way and the other going in this way, and their relative movement is going in this way. Okay, so this particular relative movement is only necessary to produce the shock wave. Okay, to produce the shock wave, but as it is suffering some sort of hindrance over here when it is striking the leading edge, okay, and getting diverted into two directions, so the energy is decreased, and then the rest of the energy which flows with rest of the energy when the air flows over the surface that is not having that amount of energy or that amount of speed to produce the shock wave, okay. So that's the reason this type of structure has been put in the wing configuration. Then we have compressibility buffet. What is compressibility buffet? It is a very simple thing. Whenever air will be compressed due to very high speed at supersonic level, so that compressed air will cause a lot of buffering or rather lot of vibrations to take place around the structure, and those vibrations can sometimes be even fatal. That may even lose control of the aircraft by the pilot, and the aircraft can come down sometimes and crash. So these compressibility buffets needs to be lowered, and we have already studied in the previous slides and in the part 1 also that any buffering or any vibration needs to be balanced by mass balance or CG balance, okay. CG has to be kept away from the hinge point so that it is balanced properly and it doesn't buffer, okay. This direction is given over here to show you that this is a venturi through which if sonic airflow comes in, that is any airflow whose speed is more than the speed of the sound, then the converging section will do what? That will decrease the velocity and increase the pressure and density, and in the diverging section the opposite will take place, that will increase the velocity, decrease the pressure and decrease the density. And just know, don't get confused with the subsonic or the sonic part. In the sonic case of a venturi, it is just the opposite, okay. It is just the opposite. The speed increases in converging range and the speed decreases in diverging range, and the other things automatically takes place in the opposite direction, okay. So in the supersonic and in the subsonic, the venturi effects are different, totally different. There is another small point which is about the aerodynamic heating. So what is this? Basically this is a air friction taking place on the surface of the aircraft. So whenever we are flying with such high speed, we know the air molecules will be striking the surface of the wing, and that will cause a lot of friction, and due to that lot of friction a lot of heat will be generated, and that heat needs to be minimized whenever we are designing an aircraft. The engineers need to keep that in mind, that a lot of heat cannot be produced, because already 2 cases were found where the Blackbird aircraft and the Concorde aircraft with 3.5 Mach and 2.5 Mach speed, even in the Concorde aircraft the speed was decreased to 2 Mach later on due to huge heat being produced on their surface, okay, due to that huge air friction taking place at that very high speed. So aerodynamic heating is basically a heating phenomena takes place due to the air friction when the aircraft passes through the air particles at that high speed or above sonic speed. That is not the case in sonic level or subsonic level, okay. That is only in the case of supersonic level. And there is also another small point which is about area rule. What is area rule? Area rule is basically that whatever the lifting surfaces we are making, we should not only think about making the wing as the lifting surface, we should think about making the horizontal stabilizer as a lifting surface. Even we should think about making the fuselage, okay. The fuselage structure should also be given some streamlined shape, where some streamlined shape like this, where it can actually generate some sort of lift. So the entire aircraft area should be used to generate lift, so that will be a better output, okay, where the entire area of the aircraft generates lift. It is not only the responsibility at that time for the wing to generate lift, it will also become the responsibility of the fuselage, the wing and all other things which are exposed to the air to generate lift and decrease the drag, okay, and generate more and more amount of lift. So it is a design criteria that the engineer needs to keep in mind while designing the aircraft. And probably there is a last slide for submodule 2 where we have to read about the engine intake airflow. In engine intake airflow in case of subsonic aircraft is a divergent, because in a divergent flow in subsonic range we know that any divergent flow, over here you can see it's given, the pressure increases. So whatever the disturbance that has happened with the air which was coming from the front and after striking the inlet, so it has lost some sort of energy. So that energy is regained when the when that airflow actually passes through this divergent duct, so the pressure increases. So increasing the pressure energy actually gives those lost energy to recover, and that is also called as ram recovery, also called as ram recovery. Sometimes these you can get in engine syllabus when you read about engine intake or engine inlet section. This process is also known as ram recovery, and the same is also true in case of a supersonic aircraft, where they don't have a diverging duct, they have a first converging duct, which actually decreases the speed. As we know, in converging section in case of supersonic, we have seen in the Venturi just now that the speed decreases. Okay, so they basically decrease the speed and make it sonic or below sonic, and then that below sonic thing passes through divergence section just like this. It becomes like this then, and through this divergence section again the pressure increases, because now this is in subsonic range. Okay, so the pressure increases, and that again gives ram recovery and increases more pressure, which will be beneficial for the compressor to work properly. Okay, so that's all about the submodule 1. If there is any doubt, and see, this was a division class, so I have just touched the points very fast. So if you find anything needs to be discussed in a better way or anything by anyone, you can tell me that. I'll try my best to do it, and I'll try to come up with questions after this as fast as possible, and after completing maybe 1 or 2 more submodules, and together we'll come up with questions, so that will be easier for you to understand. I'll also give the drive link in the description section also. It's the same drive link. If you just go over there one by one, all the submodules will be provided over there, and along with all the question papers that you require, and the books that I'm following, and some notes if required will be given. So just keep following and keep revising. If you find any doubt, just let me know. Okay, thanks for today, and kindly wait for submodule 2 to come up. Thank you.